Hello students, in our last class what we have seen is the derivation of Gauss's law. We have started with module number 2. Okay, so we have derived the mathematical model for Gauss's law. We have seen the conditions, three different special cases where what will happen to the Gauss's law equation when the charges are placed outside the surface area, like that. So in this particular session the agenda is the applications of Gauss's law. Okay, we need to see the applications of Gauss's law. So in this session let us take up two things. One is field at a point due to infinite line charge and infinite surface charge. Field at a point due to infinite surface charge. You can ask, sir, we have derived already these two mathematical model in module 1 itself. Yes, of course. So we have derived the mathematical model for the field, electric field intensity at a point due to infinite line charge of uniform distribution and infinite surface charge of uniform distribution already. You have done with the derivation. But now the agenda is we need to apply Gauss's law in order to obtain these two equations again. Okay, we need to deduce Gauss's law in order to find out the electric field intensity at a point P for these two considerations. Okay, we have to see for the volume distribution also. In this particular session let us take up these two. Okay, so the first thing is field at a point due to infinite line charge which is uniformly distributed. We need to deduce Gauss's law in order to find out the field at a point due to infinite line charge. Okay, for that we need to consider a infinite line charge along the line AB. Consider infinite line charge along the line AB. The charges are uniformly distributed along this line. Charges are uniformly distributed throughout the infinite length. In order to apply Gauss's law, what we need to do? We need to have the closed surface. We need to have the closed surface in order to apply Gauss's law. But here we have infinite length line charge. The charges are uniformly distributed. Hence, the line charge density is rho L. Rho L means line charge density, which is defined as the charge per unit length. Okay, so the infinite length line charge is given in this fashion. In order to apply Gauss's law, we need to consider a closed surface. The closed surface which we are going to consider in this particular case is a cylindrical closed surface. You can ask, why the cylindrical surface only? Why not sphere? Why not other type of polygons? Since the cylindrical surface calculations are simpler, the mathematical model for cylindrical surfaces are simpler, that's why we are assuming cylindrical surface around this line charge. Got it? So let us imagine a cylindrical surface around this line charge. Let us imagine a cylindrical surface around this line charge. Okay, so which is imaginary thing, which is not present physically. It is a imaginary cylindrical surface which surrounds the line charge. Got it? Okay, see, the radius of this cylinder is considered as R. The radius of this cylinder is considered as R. That means the distance between line charge and surface of this cylinder is also equivalent to R. Got it? The radius of this cylinder is equivalent to the distance between line charge and the curved surface. curved surface. Since a cylinder is a three-dimensional one, so this area is a curved surface area. Got it? Now let us consider an elementary surface, curved surface on this cylindrical area. Let us consider an elementary surface area on the curved surface of this imagined cylinder. Let it be ds. ds is the elementary surface area, and d is the flux density which is normal to this surface area, cylindrical surface area, where d is the flux density which comes out as a normal to this cylindrical surface. In other words, we can say a cap r unit vector is also normal to this surface, and n cap is also normal to the cylindrical surface. We know that electric field intensity, electric flux density, unit vectors all are in the same direction. That's why, which are all normal to the surface of this cylinder, cylindrical shape. This cylinder itself, imaginary thing. This imaginary cylinder is considered as Gaussian surface. Gaussian surface. Okay. Since it is an imaginary cylindrical surface which is considered around the line charge, this is called as Gaussian surface. What is the length of this line charge? Length of this line charge is assumed to be L. L is the length of the line charge within this cylinder, imaginary cylinder. This is the geometrical consideration we need to have to proceed with the derivation. What is the agenda of this derivation? We need to derive the equation for field at a point due to infinite line charge which is uniformly distributed by using Gauss' law. Okay. So according to this geometrical consideration, so elementary flux density, elementary electric flux due to elementary surface area is given by d dot ds. We have seen in the previous class, already we have this equation. We have seen all this mathematical model in the previous two classes, right? Elementary flux, electric flux due to elementary surface area is given by this equation. But we know that since d is in the form of vector, this can also be written as d into a cap r. d into a cap r. Also we know that ds is equal to ds dot n cap. Also we know that ds, this vector, is equal to ds dot n cap. What is n cap and a cap r? A cap r and n cap both are unit vectors which are normal to the surface of this cylinder. Got it? Now substitute these two quantities into the above equation. Therefore d psi becomes d a cap r dot ds into n cap. Rearranging this equation, d psi is equal to d into ds into a cap r dot n cap. What is this quantity a cap r into n cap? According to the previous discussion, since these two are unit vectors, a cap r into n cap is equal to 1 because these two are unit vectors, the magnitudes are 1, the difference, the angle between these two is 0, hence the magnitude is equal to 1. Got it? Therefore the equation becomes d psi is equal to d into ds only, d into ds. In order to obtain the total electric flux over the entire curved surface, in order to obtain total electric flux psi, This is total electric flux through the entire curved surface. Let it be psi 1. Psi 1 is the total electric flux through the entire curved surface. In order to find that, we need to integrate psi 1 is equal to integration of d psi. We need to integrate all the elementary areas throughout this curved surface in order to obtain the total electric flux throughout this curved surface of this cylinder. So we need to perform this. Therefore, psi 1 is equal to integration of d into ds. Got it? Since d is constant, since this d is constant throughout this curved surface, then we can take it outside, d into integration of ds. Since d is a constant quantity, because the electric flux density is constant throughout this curved surface of this cylinder, imaginary cylinder. Hence, it is taken outside the integration. So, integration of ds becomes the area of this cylinder. Integration of ds is equivalent to the area of this cylinder. What is the area of the cylinder? Area of the cylinder is equal to 2 pi r into L. According to the geometrical shape, area of the cylinder is equal to 2 pi r into L. So let me write here. Integration of ds is area of the cylinder. Hence, the equation becomes like this. Psi 1 is equal to d into 2 pi r into L. Let it be equation 1. Name this as equation 1. Now, let us consider the second consideration. Okay. So, we have two more surface in this imaginary cylindrical shape. Which are those? So, there is a flat surface on the top and there is a flat surface on the bottom. Okay. You need to imagine a cylinder, perfect cylinder, three-dimensional cylinder. So, in a cylinder, we have curved surface area and a flat top surface and flat bottom surface. Now, the assumption is the electric flux density, the electric flux produced by the top surface area is psi 2. The electric flux produced by bottom flat surface is psi 3. The electric flux produced by this curved surface is assumed as psi 1. So we have calculated already psi 1. We need to calculate psi 2 and psi 3 in order to obtain the total electric flux psi. Right? So which can be written as the total electric flux from this geometrical shape, from this geometrical arrangement is equivalent to psi, which is psi 1, the flux due to the curved surface area, psi 2, flux due to top flat surface, plus psi 3, that is flux due to bottom flat surface. Okay, we need to calculate this one. Okay, now psi 1 is calculated in this fashion. In order to calculate psi 2, that is electric flux due to top flat surface of this imaginary cylinder, now you need to consider the same equation, that is d psi, the elementary, consider elementary surface here, consider elementary surface ds here. So therefore d becomes d dot ds, again d psi is equal to d dot ds, the same equation we can consider. Okay, now assume here the same equation holds good. Therefore, d psi can be written as d into ds into a cap r into n cap. The same equation we can write. Okay, but here the difference is, see, if we shift this elementary surface area into the top of this cylinder, then n becomes 90 degree to this D. Got it? N becomes 90 degree, right angles to A cap R and D. Therefore, see, look at this arrangement. So D cap and A cap R is in this direction. If we shift this elementary area onto the top of this flat surface, then N cap is in this direction. N cap is in this direction. Therefore, it creates 90 degree. Okay, which creates 90 degree between N cap and A cap R. Therefore, the dot product becomes A cap R dot N cap is equal to magnitude of A cap R into magnitude of N cap into cos theta. According to dot product of two vectors, this equation holds good. Magnitude of these two vectors into cos theta. So what is theta? Theta is equal to 90 degree. What is cos 90? Cos 90 is 0. 0 into 1. Magnitude of these two is 1 because these two are unit vectors. Therefore, A cap R into N cap is equal to 0. Since this quantity is 0, d psi becomes 0. Therefore, in order to obtain psi 2, we need to integrate all the d psi here. Therefore, psi 2 also 0. The electric flux due to the top flat surface is 0. The same thing holds good for bottom flat surface also, because if I consider an elementary surface ds on the bottom flat surface, again n cap is normal to the A cap R. N cap is normal to the A cap R, which forms another 90 degree here. Therefore, the angle between these two becomes 90. Therefore, the flux produced by these two are orthogonal, hence it is 0. Since the same considerations holds good for bottom flat surface also, psi 3 is equal to 0. Psi 3 is equal to 0. Hence substituting all elementary things, psi is equal to psi 1 plus psi 2 plus psi 3. What is psi 1? Psi is equal to, psi 1 is d into 2 pi r into L plus 0 plus 0. Therefore, total psi is equal to d into 2 pi r into L. Name this as equation 2 again. Okay. And according to Gauss's law, what we have seen, the electric flux is equivalent to the charge enclosed within it. Electric flux from a closed surface is equal to the charge which is enclosed within the closed surface. We have seen this. We know that the charge enclosed within the closed surface is equal to charge density into length of the charge, length of the surface. Okay. Now psi is equal to q is equal to, what is charge density for this particular case? The charge density is assumed to be rho L. Rho L is the charge density, line charge density of this infinite length uniformly distributed charge. Okay. Then charge density is considered as rho L. What is the length we have considered? L is the length of the cylinder. Length of the cylinder is L. Therefore, this is L. You can ask the doubt, what about other than this cylinder? We need to, since the length of this line charge is infinity, So it is from plus infinity to minus infinity. We are considering the length as L. What about other charge distribution? We no need to consider that distribution, because according to Gauss' law statement, the charge which are outside the enclosed surface, outside the closed surface, does not contribute to the flux, right? So no need to consider the charges which are present outside this geometrical arrangement, outside this surface, outside this closed surface, because the charges which are contributing into the flux is zero, negligible. Okay, so according to that fact, psi is equal to Q, which is equal to rho L into L, and the charges which are outside the surface is zero, because it contributes zero to the flux. So name this as equation 2. Equation 3. So equating equation 2 and 3, what you are going to get? D into 2 pi R into L is equal to rho L into L. L gets cancelled. Okay, then D can be written as epsilon naught into E into 2 pi R is equal to rho L. What we need to do? What is the agenda? Electric field at a point due to the infinite line charge. We need to solve this equation for E. Therefore, E is equal to rho L divided by 2 pi epsilon naught into R. This is the equation which we have derived already. Okay. If we want to represent the same equation in terms of vector, let me write here. In terms of vector, E is equal to rho L divided by 2 pi epsilon naught into R into A cap R. See, we have started with Gauss' law by considering flux density and elementary flux due to elementary surface area, but we have ended up with electric field intensity. Therefore, we can say Gauss' law can be applicable to calculate the field, electric field at a point due to infinite line charge. In this particular case, you need to remember three things. One is electric flux lines are normal to the surface. So when we choose the elementary surface, accordingly the angle of the unit vectors are going to change. Those angles plays prominent role towards the flux density calculation. You need to remember all those things. And one more important thing is the charges which are present outside the imaginary surface considered are neglected, because the contribution to the electric flux is not taken. Okay, so this is how the application of Gauss' law towards the field at a point due to a line charge. So let us start with the next derivation, field at a point due to surface charge, infinite surface charge. Okay, let us start with the next topic. So field at a point due to uniformly charged infinite surface area. So the previous one is infinite linear charge, line charge. Here infinite surface charge. So let us consider a infinite arbitrary shape, infinite surface of uniformly charged area. Uniformly charged infinite surface area has been considered. Now let us assume an imaginary cylinder. Let us assume an imaginary cylinder Let us assume an imaginary cylinder which is passing through this surface. Okay, so which is symmetrical on either side of this surface, which is symmetrical on either side of this surface. Hence, the distance from the center and point P is R. Distance from center of this surface to the point P is R. The same distance has been considered in other side also, because it is symmetrical on either side of the surface. You need to assume this closed surface, because we are applying Gauss law. So Gauss law is applicable only for the closed surface. Got it? So now let point P be the arbitrary point chosen where we need to calculate the electric field intensity. Okay, so here the point P is assumed at the edge of this imaginary cylindrical shape. Point P is assumed at the edge of the imaginary cylindrical shape. Okay, let ds is the elementary area considered. Let ds is the elementary area considered at the flat end of the imaginary cylinder. So this is the flat end. Again, this is the flat end. This is the curved surface. This is the curved surface. Along this line, this is the curved surface. Now, the electric field intensity D is in this direction. In the same way, A cap R is also in this direction, and N cap also in this direction, because all these are in the same direction to this electric flux density. Got it? Now, in order to calculate the electric flux, elementary electric flux due to this elementary area, we need to consider the same equation. What is that equation? D psi is equal to D dot ds. The same equation we need to consider. We know that D is equal to D into A cap R. ds is equal to ds into N cap. Substitute these two into the above equation. What you are going to get? See, d psi is equal to d into ds into A cap R into N cap. Let A is the area of this flat surface. Let A be the area of this flat surface. And again, A is the area of this flat surface. Okay. Then d psi is equal to d into ds, because A cap R and N cap is equal to 1. Magnitude of these two is equal to 1. So then d psi is equal to d dot ds. Got it? Keep this equation as it is. Now, in order to obtain psi 1, let it be psi 1, the electric flux due to the flat surface. This is psi 1. Electric flux due to flat surface 1 is psi 1. Electric flux due to flat surface 2 is psi 2. Electric flux due to the curved surface is psi 3. Electric flux due to the flat surface 1 is psi 1. Electric flux due to flat surface 2 is psi 2. Electric flux due to curved surface is psi 3. Now psi 1 we are calculating. Psi 1 is equal to integration of all the elementary surfaces. That is, psi 1 is equal to integration of d into ds. We know that d is constant for this particular flat surface. Therefore, psi 1 is equal to d into integration of ds. What is this integration of ds? If we consider the entire flat surface, which becomes area. So area of this flat surface is A. Then psi 1 is equal to d into A. Because integration of ds is considered as area of the flat surface, where A is the area of flat surface. Okay. The same explanation holds good for psi 2 also. What is psi 2? Psi 2 is the electric flux due to another flat surface on other side of the charged surface area. That is psi 2 is equal to integration of d psi, that is psi 2 is again equivalent to d into A. Then what about psi 3? We need to calculate psi 3, that is electric flux due to the curved surface area. What is psi 3? Flux due to curved surface. Flux due to curved surface. How to calculate psi 3? In order to calculate psi 3, let us consider the elementary surface ds on the, let us consider the elementary surface ds on the curved surface of this cylinder. So for this consideration, the n cap is perpendicular to the direction of a cap r. N cap is in this direction. So which forms angle theta, which is 90 degree to the direction of a cap r. Got it? So if I consider elementary surface on the elementary area on the surface of this cylinder, so which is normal to the surface of the cylinder, n cap is normal. Since it ejects normal to the surface, it forms an angle theta which is perpendicular to the elementary, so the direction of electric flux density as well as unit vector, direction of unit vector a cap r. Therefore the elementary flux d psi is equal to d into ds into a cap r into n cap equation becomes 0, because d psi becomes 0 because a cap r into n cap is equal to 0. Why it is 0? According to the dot product, cos theta, cos 90, theta is 90 degree, cos 90 is 0. Therefore a cap r dot n cap is equal to 0. Substituting this into the above equation, d psi becomes 0. So psi 3 is equal to integrating all d psi values, therefore psi 3 also 0. Therefore the contribution of the area on the surface of this imaginary cylinder towards the flux is 0. That is what we need to have. Now substituting all the values in order to calculate total electric flux, psi is equal to psi 1 plus psi 2 plus psi 3. Therefore psi is equal to, what is psi 1? dA. What is psi 2? dA. What is psi 3? 0. Then psi is equal to 2 dA. Name this as equation 1. Now according to Gauss's law, psi, total electric flux, is equal to the charge enclosed within it, which is given by, for this particular geometrical consideration, charge density into area, charge density into surface area. Therefore psi is equal to Q is equal to, what is the charge density for this surface area? Charge density is rho s, charge per unit surface area, into, what is the area we have considered for the flat end? A is the area we have considered. Name this as equation 2. Equating equation 1 and 2, what you are going to get? 2 into d into A is equal to rho s into A gets cancelled. 2 into d can be written as epsilon naught into E, which is equal to rho s. We need to reduce this equation for E is equal to rho s divided by 2 epsilon naught. This is what the electric field intensity due to infinite surface charge of uniform charge distribution. If we represent this in vector form, E is equal to rho s divided by 2 epsilon naught into a cap r. Therefore, the conclusion is Gauss' law can be useful in order to find out the electric field due to n number of charges, n number of types of charges, line charge, surface charge, volume charge, and so on. Got it? Thank you.